This is a walkthrough of a Further Mathematics AS Decision Maths 1 paper. Question number 1. The following algorithm determines the total number of comparisons required when Prim's algorithm is applied to a complete network on n vertices where n is greater than 2. And we've got a list of 10 steps in this algorithm. Now, for the first part of part A, it says for the case when n is equal to 6, complete the table in the answer book, so that's this table here, or part of the table, to show the results obtained at each step when the algorithm is applied. Right, so we start with step 1, and step 1 says input the value of n, and the value of n is 6. So we'll put 6 in the table. We'll move on to step 2. It says let a equal 1, so we'll make a equal to 1. Then we move on to step 3, and then step 3 says let b equal n minus 2, so that will be 6 minus 2, so b is going to be 4. Then step number 4, that says let c equal b, so c is going to equal what b is, so that's going to be 4. Step number 5 says let a equal a plus 1. Okay, so this needs to go on the next row. So if a is going to be a plus 1, we would add 1 to a. So that now becomes 2. Step number 6, that is let b equal b minus 1. In other words, we just take 1 away from b. So we have 3 in the table there. Now when we get to step number 7, we've got a calculation that we need to do. And it says let c equal c plus a times b plus a minus b. Okay, so let's write that calculation out. So c is going to equal what c currently is, which is 4, plus a times by b, that's 2 times by 3, plus a, which is 2, minus 1. That gives us 4 plus 6 plus 1. So c is going to be 11. So we'll put the 11 in the table. Moving on, then next step, it says if step 8, if b is greater than 0, go to step 5, otherwise step 9. Now b is greater than 0 because it's 3, and then we need to record it in the table here. Is b greater than 0? So we'll just write down yes. So at this point, we're going to go back to step number 5. Step number 5 says let a equal a plus 1. So we increase a by 1, it now becomes 3. Next step, step number 6, it says let b equal b minus 1, so we decrease b by 1, it now becomes 2. And then step number 7, we have that calculation for c again. So c is now 11. A and b, they are now 3 and 2. So 3 times 2 is going to give us 6. And a, that's 3. So we get 11 plus 6 plus 2, which gives us 19. So now c is now got value of 19. Step number 8, if b is greater than 0, yes it is, so that means we're going to just jump back to step number 5 and record that in the table by writing yes. Let a equal a plus 1, so a now becomes 4. Step 6, b equal b minus 1, so b now becomes 1. Step 7, we do the calculation to calculate the new value for c. So now c is going to be 19. A is now 4. So we'll have 4 here and 4 here. And b is 1. So c is now 26. B is still greater than 0, so we record yes, and we jump back to step 5. Step 5, we increase a by 1. Step 6, we decrease b by 1, so it's now 0. Step 7, calculate this new value of c, and that will give us new value of c of 30. So that goes into the table. Step 8, if b is greater than 0, Go to step 5. Now here b is not greater than 0, it's actually equal to 0. So we recall that in the table as no, b is not greater than 0. So then we go to step 9. So step 9, we output c, which is going to be that value of 30, and then we stop. Now the second part of part A says state the final output, so we just need to write it down. So the final output is that value of c, which is 30. Here we've got f of n is equal to 1/6 n cubed plus kn plus 1 for n in a set of natural numbers where n is greater than 2. The function f of n gives the same output as the algorithm. Part B, determine the value of k. Well, the algorithm, when n was 6, it gave us an output of 30. So what does that mean? Well, it means for this function that if I put 6 into the function, so make n equal 6, I should get an output of 30. So let's substitute in the 6. So f of 6 will be 1/6 times by 6 cubed, replacing n with 6, plus k times 6, or 6k, plus 1 is equal to 30. So when n is 6, the output is 30. So let's simplify this down. So 1/6 of 6 cubed is 36, plus 6k, plus 1 is equal to 30. So now we can rearrange this for 6k equal to, and that will give us -7, so 30 minus 1 minus 36. So that will give us a value of k of -7/6. Part C, by considering f of n, the function here, state what can be inferred about the efficiency of Prim's algorithm. Now, since f of n, this function of n, is cubic, that's the largest power, that we can infer from that that the order of Prim's algorithm is cubic, or it has cubic complexity. That's another phrase you could use instead of this. Question number 2. The weights on the arcs in figure 1 represent distances, and the total weight of the network is 88. Part A, and part 1 of part A, use Dijkstra's algorithm to find the shortest path from A to J. Okay, so we'll start with our start vertex here. So that's always going to be the first one that we label, because we can put in the final value straight away, and that's going to be 0. We next look at the vertices which are directly connected to that vertex, the one with the lowest weight, which is going to be 0 anyway. And then we can put in some working values of 0 plus 5, which is 5, and 0 plus 8, which is 8. I pick the vertex that has the lowest working value, and that's going to be B, which has 5, and I'm going to make that the final value, so this will be the second vertex that I label. I then look at the vertex or vertices which are directly connected to B, and that's only C, and so I can work out C's working value, so that's going to be 5 plus 2, so that gives me 7. Now C is the only vertex with working values, so 7 is going to be the lowest because it's the only value, so that becomes its final value, and this will be the third vertex that I label. Now the vertices directly connected to C, which have not yet got final values, are going to be G, D and F. So now we can work out what their working values are. So the final value of 7 plus 5 gives me 12 for G. And then if I look at vertex D, so that's going to be 7 plus 7, that's going to be 14. And then for vertex F, that's going to be 7 plus 9, which is 16. Out of those first 3 vertices, G has the lowest working value, so that's going to become its final value of 12, and this is the fourth vertex that I've labelled. The vertices directly connected to G, which have not yet got a final value, are F and H. So 12 plus 4 will give H a working value of 16. And then 12 plus 3 will give F a working value of 15. The vertex that has the lowest working value from D, F and H is D, so the 14 becomes its final value, and that will be the fifth vertex that I label. The vertices directly connected to D are E and F, so a working value for E is going to be 14 plus 4, which is 18, and then a working value for F, or another working value, is going to be 14 plus 11. Then there's no point writing that down because that's going to be higher than the working values I have here. So I picked the lowest working values. I've got 16, 15 and 18 to choose. So it's going to be F. So F, its working value now becomes its final value. And this is the sixth vertex that I've labelled. So now I look at the vertices directly connected to F, which don't have final level labels. So H, for example, now this would be 15 plus 8 would be 23. So there's no point writing that down because it's higher than the working value of 16. If we go to J, so we're going to do 15 plus 7, that will give me 22 as a working value for J. And then for E, I'll get a working value of 15 plus 2, which is 17. Now, out of those three vertices, H, J and E, H has the lowest weight or distance, so I make its working value its final value, and that'll be the seventh vertex that I label. Now, the only vertex that's connected to H directly, which hasn't got a final label yet, is J. So if I did 16 plus 10, that's 26. Now, there's no point writing that down because that's a higher weight than the 22 I've got there. So I now pick the vertex with the lowest working value. Out of 17 and 22, that's going to be E. So its working value of 17 now becomes its final value of 17. And this is the eighth vertex that I've labelled. Then the only vertex unlabelled that doesn't have a final value yet, that's we haven't dealt with, is the finished vertex, J. So we have a final value of 17 plus 3 is going to be 20. Now we've basically got to the end of our algorithm. This will be the last vertex that I labelled. I take the lowest value, there aren't any others to compare it with, it's got to be the lowest, and that will be the ninth vertex that I label. So I can fill in my answer with the shortest length of the shortest path, which is 20. I now need to work backwards to work out what that shortest path was. So I subtract the weights of the edges from that final value there. So 20 minus 10, 20 minus 7, 20 minus 3, and I must get the final value. So it's not H, because 20 minus 10 is not 16, 20 minus 7 is not 15, but 20 minus 3 is 17. So I know that's part of my root, shortest root. So now I do 17 minus 4, that's not 14, 17 minus 2, yeah, that's 15. So the root continues here. Subtracting the weights of these four arcs from 15, there's only one of them gives the correct answer. 15 minus 3 is 12. So that means that my shortest route continues here from F to G. So from G there is only one route really, 12 minus 5, and that does give me 7, so that route continues there. Then we do 7 minus 8, well that's not going to work, it's going to give us -1. 7 minus 2, which is correct, so we go to B, and then from B 5 minus 5 that takes us back to the start vertex there. So I guess I could write down 5 minus 5 here, which gives us the 0. So I can now write down my shortest route as A, then to B, then C, G, F, E to J. An arc of weight 6 is added to the network between nodes C and H. An inspection route of minimum length that traverses each arc at least once needs to be found. The inspection route must start and finish at A. Part B. Use an appropriate algorithm to find the arcs that will need to be traversed twice. You must make your method clear. So let's first of all add on that extra arc between C and H, which has a weight of 6. Now the first thing we need to do is to identify all of the odd nodes. So I'm going to write down the valency of each of these nodes. That basically is how many vertices come out of the node. And I want to identify the odd ones. So this one, F here, 1, 2, 3, 4, 5, 6. So that's even. H is going to be 1, 2, 3, 4. So that's even. G, that's 3, so that's going to be odd. And C, 1, 2, 3, 4, 5, 6. Okay, I think that's all the nodes labelled, the vertices labelled. So the odd vertices are, let's do it in alphabetical order. So it looks like D, E, G, J. D, E, G and J. We now need to list the pairings of these vertices, and the pairings are going to be D and E, G and J, then D and G, and E and J, and then lastly D and J and E and G. So if you've got 4 odd vertices, you're always going to have 3 pairings. Now what we need to do is to find the shortest routes between these vertices. So let's take all of this off, we don't need these anymore. So D to E, okay, D to E. Now the shortest route between D and E is 4. And then G to J. Now I think the shortest route from G to J goes G, F, E, J. So it's 3 plus 2 plus 3, which is 8. So giving a total weight of 12. Then D to G. So D to G. Again, want to find the lowest weight. Now that looks like this one. 4, 2, 3. So that will give 9. And then E to J, well, I can see that's just 3. So that also has a weight, minimum weight of 12. And then D to J, so that's going to be along here, D, E, J, so that's going to be 7. And then E to G, so E to G, okay, that's just going to be this 2 and a 3 here, so 5. So this also has a weight of 12. Now normally what you do is you'd pick the pairing with the lowest weight. Since all pairings have the same weight, we can pick any pairing. So I'm just going to pick the first one. Yeah, D, E and D, G, J. So D to E, that was 4, so that was this route. So this is going to be doubled up. So let's just put that on our diagram here. So another weight of 4. Then to get from G to J was along this route, wasn't it? It was G, F, F, E, E, J. So let's double those up. So we're going to need to double this up. So another 3 here, another 2 here, and another 3 here. So that means that arcs DE, EF, FG and EJ will need to be traversed twice. Part C, determine the length of the inspection route. So the original network had a weight of 88. This extra arc, which I've done in dark red, was added. So that adds another weight of 6. Then we've got these arcs, which are going to be traversed twice, and they have a total weight of 12. So the total weight of this new network is going to be 88 plus 6 plus 12, which gives me 106. Question 3. A project is modelled by the activity network shown in figure 2. So this diagram here. The activities are represented by the arcs. The number in brackets on each arc gives the time in days to complete the corresponding activity. Each activity requires exactly one worker. The project is to be completed in the shortest possible time. Before the project begins, the duration of activity G in days is unknown and is given by X, where X is greater than 8. So I can see that here. Part A, complete diagram 1 in the answer booklet. So that's this diagram here, to show the early event times and the late event times in terms of X where necessary. Okay, so here's a larger version of the diagram. The important piece of information I think I'll need from the written part of the question is that X is greater than 8. So we're going to start with a forward pass and write down 0, 0 in the first box. That's always what we do. And then we're going to work forward along each arrow. So let's look at what we're going to put here. So we've got an activity length of 5. There aren't any other ways of going forwards to get to this box here. So we're going to have 5 as the earliest we can get to that point. Let's fill in C next. So again, only one way to get to this point here along activity C. So the earliest I can get to that point is also 5. Now when we get to this point here, there are 2 ways of getting to A. There's this route, which is along the A, which is a length of 3, or there's this route, the 5 here. Now this dummy doesn't carry any weight, so I've got a choice between 5 and 3, and we always take the highest value as the early event time. So here I'm going to have 5. Let's move along. So continue with our forward pass. Only one way going forwards to get to this point here along activity D. So 5 plus 6 will give me 11 here. Now when we get to this point here, there are 3 ways of getting to this point. Either along E, which would be 5 plus 8, which is 13, or at this point 5 plus 4, which would be 9, or this way, which would be 11 plus X. So 11 plus X. And I need to choose the highest of those 3 values. Now since X is greater than 8, 11 plus X is going to be greater than 19, isn't it? So it's definitely going to be the largest value. So that's going to be 11 plus X that I write in this box. So 11 plus X. Now we continue our forward pass. I'm going to go to this point here. There's only one way going forwards to get to here, and that's going to be 11 plus X plus 5, which will become 16 plus X. And then I will complete this one here. Now there are 2 possible ways of getting here. So the 11 plus the 4, which will give me 15. Or this way, a dummy carries no weight. So this would be 11 plus X. The 11 plus X we know is greater than 19 because the X is greater than 8. So I'm going to have 11 plus X here because that's the largest of those 2 values. And then we'll move to this point here. So there are 2 ways of getting here. The 16 plus X and the 11 plus X. So the 16 plus X is the larger of the 2. So 16 plus X. And then we reach the final boxes at the end. So coming along the top, 16 plus x plus 3 is going to be 19 plus x. Along the middle path, 16 plus x plus 5, which will be 21 plus x. And then along this bottom route here, along activity L, 11 plus x plus 6, which is going to be 17 plus x. And again, we pick the biggest of the three, and that's going to be 21 plus x. Okay, so now we're going to complete our backward pass, which means going backwards along all the other arrows, subtracting the event length time, and then taking the lowest of possible values as I work backwards. So I'm just going to put some arrows going backwards, so I know which directions I'm going in, so I don't make any mistakes, because it can be easy. Sometimes I end up going forwards along an arrow when I shouldn't do. So this is just going to help me remember which direction I'm moving in. I think that's all the arcs done. Right, okay, so in the end box we put the late event time equal to the early event time, and let's work backwards. Let's go along here. So this is going to be 21 plus x minus 3, and so that's going to give us 18 plus x if we take this top route here. There is another route backwards to get to that point, but we need to fill this one in first. So going backwards, there's only one route here, so this is going to be 21 plus x minus 5, and that's going to give us 16 plus x. So we'll put that in. So now we can work out what to put here. So here, this is also, this has no weight, so this is going to be 16 plus x here as well. So these are my two choices. I take the lower of the two, so yeah, that's also going to be 16 plus x. Okay, what I'll do is I'll rub out those routes that I've already done and work backwards along. And yeah, there's two ways of getting here. Either along here, 21 plus x minus 6, so that will be 15 plus x if we take this route, or if we take this route, dummy, no weight, no time, no duration, so 16 plus x. I take the lowest of the two, so 15 plus x. So I can rub these out. Let's continue, and we'll go back along here, and then we've got that one to do, backwards along here and backwards along here. So we'll go to the top here. So we've got 16 plus x minus 5 if we take this route back, and that's going to be 11 plus x. But I also have this way of getting to this point. Now there's no weight on here, so that will give me 15 plus x. If I work backwards along here, I take the lowest of the two, that's going to be 11 plus x. And then I've got some things to rub out here, so 11 plus x. So we can take that out, we've done that. And we can take out this arrow as well here. So if we work down here, this is going to be 11 plus x, and then we take away the x, so the root coming in from the top will give us 11. And then here it's going to be 15 plus x minus 4, that'll be 11 plus x. Now 11 plus x, well, that's going to be bigger than 11. We take the smallest one, so in here we're going to put 11. Okay, so we can get rid of these here and continue back. I think the easiest one is going to be here, because there's only one route back into that, so that will be 11 minus 6, which is 5. Then working along here, this will be 11 plus x minus 4, which is going to be 7 plus x. There aren't any other routes there, so that's going to be my late event time. Okay, so that arrow's gone. So we're now working backwards into here. There are two ways back here. Either the 7 plus x There's nothing to subtract from 7 plus x. Or here, this will be 11 plus x minus 8, which is going to be 3 plus x. The smallest of those is 3 plus x. So that's our late event time. So we can take that working out and a bit of the x that I rubbed out. And then we're just now working back just to check. And it looks like it's going to be this event minus the actual time here, the duration, to give us 0. None of these other ones will give us 0. So when it comes to critical path, it looks like we're going to be looking at this event here, or this point here, as part of the critical path. Part B, we need to identify the critical activities. So the first thing I've done is to identify those boxes where the numbers at the top and the bottom are the same. That's the first thing we need to do. And then we need to look at the activity that's between them, and we need to see if the value of the activity, the length of time, is the same as the difference between the two numbers at the end. So the difference between 5 and 0 is 5. Okay, so that's going to be part of our critical path. The distance between 5 and 11 is 6. Okay, or 11 minus 6 gives you 5. Okay, how about up here? So 11 plus x, yeah, is 11 plus x. So that's part of it as well. So 11 plus x plus 5, yeah, that's 16 plus x. And then now when we go to this way, if we do 16 plus x plus 3, that's not 19. That's 19 plus x, which is not 21 plus x. So this is not part of the critical path. However, the dummy here, this has no weight, so we should still end up with 16 plus x. And then 16 plus x plus 5, yeah, that's 21 plus x. So our critical activities are C, D, G, H, and K. Part C. The sum of the total float for activity A and the total for the float for activity E is equal to the minimum completion time of the project. Part C. Making your reasoning clear, determine a minimum completion time for the project. So let's start by working out these floats for A and E. Now remember, the float is the late event time minus the activity length minus the early event time on the other side. So here, for A, we're going to do 7 plus x minus 3 minus 0. Okay, so the float for A is that 7 plus x, that late finish time, minus the activity length, which is 3 minus 0, and that gives us a value of 4 plus x. Then we're now going to work out the float for E. Float for E. So let's have a look at E. E is here. So it's this late finish time. So it's 11 plus x minus the activity length, which is 8. And minus the early event time here, which is 5. So that gives us minus 2 plus x. And we're told that this is equal to the minimum completion time of the project. And the minimum completion time is 21 plus x. So we want the sum of these two floats. So that's the float for A, which is 4 plus x, plus the float for E, which is negative 2 plus x. and that is equal to the minimum completion time, which is 21 plus x. So if we put this all together, we'll have 2x plus 2 is equal to 21 plus x. So it's just about solving this. So if you take x away from both sides, we'll have x, and then if we take away 2 from both sides, we'll get x is equal to 19. So we've got the value of x. We need to determine the minimum completion time. So minimum completion time will be 21 plus x, that's 21 plus 19, and so that's going to be 40, and it's in days, because right at the beginning of the question it talks about days, these numbers here standing for days. Okay, so let's just highlight those answers: critical activities and the minimum completion time. Question 4. A baker makes lemon cakes and cherry cakes for a forthcoming fair. Lemon cakes, cherry cakes. The baker must make at least 360 cakes in total. The cost of the ingredients for each lemon cake is 40 pence. So lemon cake is 40 pence. And the cost of the ingredients for each cherry cake is 20 pence. So cherry cake, 20 pence. The baker has a total budget of £200 to spend on ingredients. The baker must make at least twice as many cherry cakes as lemon cakes. So at least twice as many cherry cakes as lemon cakes. And he must make at least 100 lemon cakes. So must make at least 100 of these lemon cakes. The baker calculates that the time required to decorate each cake is 1 minute. So lemon cake's 1 minute, and the time required to decorate each cherry cake is 3 minutes. The baker wants to minimize the total time needed to decorate all the required cakes. Part A, formulate this information as a linear programming problem. So I'm going to define my variables as x is equal to the number of lemon cakes and y equal to the number of cherry cakes. And if you weren't sure which one to make x and y, you can look at the graph that goes with this question that would be in the answer booklet. So this is a minimization question, minimizing the total time. So we're going to minimize like our profit in terms of time. So we're going to be minimizing P. And the time that we have here is each lemon cake takes 1 minute. So that would be like 1x. And each cherry cake takes 3 minutes to decorate. So plus 3y, and we want to minimize that time. And it's going to be subject to some constraints, and we'll write those constraints down. So we'll go right back to the beginning of the question and we'll do the constraints as we go along. So the first thing here, the baker must make at least 360 cakes in total. So the number of lemon cakes and the number of cherry cakes must be at least 360, so greater than or equal to 360. If we continue, the cost of the ingredients for each lemon cake is 40 pence, and the cost of the ingredients for each cherry cake is 20 pence, and they have a total budget of £200 to spend on ingredients. So in pounds and pence, that's going to be 0.4 x 40 pence per lemon cake plus 0.2 y 20 pence per cherry cake, and that needs to be a maximum of their budget, so we can only go up to £200 in total. Then the next one, the baker must make at least twice as many cherry cakes as lemon cakes. So the number of cherry cakes needs to be at least twice as many as the number of lemon cakes. So it's the number of lemon cakes we times by 2, not the number of cherry cakes. and it says he must make at least 100 lemon cakes. So lemon cakes is the x, so that needs to be at least 100, more than or equal to 100. Now we also need to include constraints about non-negativity. Now if we didn't have this x is greater than or equal to 100, we would have written that x needs to be greater than or equal to 0, but this like sort of overdoes that, so we don't need to add that. But we do need to say that the number of cherry cakes needs to be more than or equal to 0. We can't make a negative number of cherry cakes. So that would be our answer for part A. So we've formulated it as a linear programming problem. And moving on to part B. Part B says this: we want to use a graphical method to determine the number of each type of cake the baker should make in order to minimize the total decoration time. You should make your method and working clear. Right, so let's go through each of our constraints here. And on the last line I'm going to put on is the objective line. So let's start with this: x plus y is greater than or equal to 360. So I know that that is going to be crossing the axis, x and y axis, at 360. So I'll mark those points on. And then what I'll do is I'll draw a line between those 2 points. Okay, now I will label them afterwards, but for now I'll just color code them. So that's the blue line. Now for this constraint here, it probably would be better if I turn these into whole numbers, just make it a little bit easier to find those points. So if I times through by 5 to make everything a whole number, or I could even multiply by 10, but the problem is that doesn't go up to 2000. Yeah, if I multiply everything by 5, I'll get an equivalent inequality, and that will be 2x plus y less than or equal to 1000. So I've just times through by 5. Okay, so let's draw this line then. So when I make x equal to 0, y is going to be 1000. So I'll mark that on. And when y is 0, x is going to be 500. So I'll mark that on as well. I guess what I should have done as well on the previous one that I plotted, because it's greater than or equal to 360, I'm going to shade off the area that I don't want, leaving the area that I do want clear in the middle. So greater than or equal to 360 would be this point above this blue line. So all of these points, the x plus y is greater than 360, all of these it's less than 360. If you're not sure, pick a test point. So if I pick 0, 0 here, which is on this side of the blue line, that's definitely not going to be greater than or equal to 360. So I'm shading off the area that I don't want. I just find that more useful than shading the area that you do want, because then you end up with sort of lots of lines in the middle that can be a bit confusing. So I'm now going to join together the points for this second inequality here. So that one I'm doing in green. So there's my line. Again, I'm going to shade off the area that I don't want. Now this is less than or equal to 1000 for 2x plus y. So that would be any of this area here. That's what I do want. So I don't want the other side, so let's shade that off here. So now we'll move on to this one. The y is greater than or equal to 2x. So we'll start by actually drawing the line y equals 2x. So I'm just going to need a couple of coordinates, 2 or 3 coordinates to get that line. Right, so for example, if I had x as 100 for this equation, then y would be 200. 2 times 100 is 200. So 100, 200. So that gives me like a little point. I think it's here. If I got that right. Squares are tiny, so it's quite difficult. Let's do another one. So let's go maybe as far as we can. So if x was 600, y would be 1200. So it's going to go right at the end, at the top corner. And I know it's going to go through 0, 0. Okay, so I'll just need to join those points up. Okay, so there's my line here. So I want to find out which side I need to shade. So if I pick, let's say 100, 100 as a test point. So if I did 2 times 100, is that less than 100? No. So actually, the side that I want is going to be this side. This side is the side that I don't want, because when I tried 100, 100, it failed that inequality. So I basically want the fail side. I want the side which doesn't work for the inequality shaded, leaving the bit that I do want on the other side. So that is this one in red. Then we've got x is greater than 100. Oh, that's a nice easy one to do, because I'll just do x is equal to 100 line. So the greater than or equal to 100 is the side that I do want. So I'll shade off the side that I don't want, which is going to be less than or equal to 100. And then the last inequality here, y is greater than or equal to 0. Let's do that in dark red. So I'll draw the line y is equal to 0, which is going to be down here. I want the side where it's greater than 0, so I'll shade off the side where it's less than 0. So I'm looking for an area where I've got no lines at all, and it's going to be this area here. So that's going to be my region R. And then last, I'm going to draw in my objective line. So to help me draw the objective line, I need a couple of points. So let's say I made P equal to 600. Then that would give me x equal to 600. And when y is 0, or y equal to 200 when x is 0. Okay, so we just need to pick a value for P, and then we get our 2 points. We can draw our objective line. So here's my objective line here, and I've labelled up all the other lines as well. So my objective line is going to be moving in this direction. Because I want to minimise, I want to find the first vertex that I'm going to encounter, and that's going to be this one here, and that is the intersection of the blue and red line, and that's the lines x plus y is equal to 360, and the red line, which is y is equal to 2x. So I need to solve those simultaneously, so that's fairly straightforward. So I can take the y is equal to 2x and put it into the first equation. So I'll have x plus 2x is equal to 360. That's 3x is equal to 360. So that's x is equal to 120. If I then substitute that into the second equation, or even just use it in the first one, 2 times 120 gives me y. So y is 240. So the baker, he should make 120 lemon cakes and 240 cherry cakes. So always give your answer in context. Don't just say x is 120, y is 240. And a quick check, these values here satisfy all of the other constraints as well. So the other constraints we haven't used, x is greater than or equal to 100, yes it is. 2x plus y is less than 1000, so 2 times 120, 240, plus another 240, yes, that is less than 1000. And lastly, part C, using your solution to part B, that's the solution we've got here, determine how much of the baker's budget for ingredients will be unspent. So if we go back in the question, they've got a total budget of £200. Now, if they're going to be making 120 lemon cakes and the ingredients for each lemon cake is 40p, so if you do 120 times by 40p, we get a cost of £48. And then if they're making 240 cherry cakes and the ingredients for each cherry cake is 20p, that also gives £48. So in total they're going to be spending £96. So from their budget of £200 they're spending 96. So the amount that they'll have left from their budget is £104.